Okay, in this video I'm going to talk about the Laplace transform, and basically when solving differential equations, the solutions containing a numbers of like unknown integration constants like a, b and c, well, the values of these constants have then been found by applying boundary conditions to the solution. Fortunately, for a certain type of differential equation, there's a method, of obtaining the solution where these unknown integration constants are evaluated during the process of the solution, and that method is called the Laplace transform. And the method hinges on what is called the Laplace transform. So let's look at the Laplace transform equation. So the Laplace transform of let's see a function is a function of t. So the Laplace transform of a function of t is literally the definite integral from 0 to infinity of what's it called e to the power minus st. S is just a constant, by the way. It could be k or a. I'm going to call it s here, and then times that function that we're taking the Laplace of d in the respective t. So let's take an example here just to prove that formula is correct. So let's say here the Laplace of the Laplace of the number 2. Here's our function, it's just a 2. I'm going to use just a small example here. 2 over s, provided that s is greater than 0. I'll tell you why. But we can prove that now by substituting all of that with this. So we've got a function here, which is 2, just a 2, because looking at the original Laplace transform formula, we've got ft here, so 2 is going to be ft. So I'm going to substitute that in that integral. So integral from 0 to infinity. So it's going to be e to the power minus st, right? Times, well, f of t is 2 here, so 2, and then dt. Well, here it's just a simple integral formula. Well, we can take the 2 out, so it's going to take the integral of e to the power minus st. And as you know, if you take substitution, integral using substitution, well, we would get 2. And then if we integrate e to the power minus st, it's just going to be simply e minus st over minus s, because that's the constant, right? That's the derivative of the power. That's the integration of exponential. You take the derivative of the power and then divide it by the exponential. And then we've got indefinite integral. So if we take, let me just zoom out so you can see. So yeah. Oh, you know what? That'd be a lot easier. So yeah, if we solve this definite integral, so we will get well, in this case, if we substitute s with 0, t with 0, infinity with t with infinity, well, we'll get 0 at this part, because any exponential to the power infinity is just 0. Minus, if we substitute that with 0, the second definite integral, well, e to the power 0 is just 1, so it's going to be 1 over minus s, right? Sorry about that, it's a bit hectic. And if we simplify that, we get, well, minus of the minus is going to be positive, so it's going to be 1 over positive 1 over s, and that would equal 2 over s. So now we just proved that the the Laplace transform of that is equal to that. And how we proved it? Well, we substituted this with the original Laplace transform. So we've got the Laplace of any number is just that number over S. If you can look at the Laplace transform table, you will see something like that. You will see if there's a Laplace of a constant, let's call that constant. Sometimes you can see A or K. I'm just going to call it K. So the Laplace transform of any number is going to be that number over S. That's just one of the Laplace transform. So yeah, that was the main idea of Laplace transform. In the next video, I'm going to talk in more detail about Laplace transform. We're going to solve more problems.